In today's video, we are going to be performing function operations. We actually are not doing composite functions in this lesson. I have moved that into the next lesson. So we are going to be adding, subtracting, multiplying, and dividing functions. We are also going to be stating the domain of each of these functions. So we have learned many different types of functions. We've used polynomial functions, we've had radical functions, we've had exponential functions. So when you are adding and performing these operations of functions, you could be using any type of functions. So I have a little table here that you should probably write down. So the addition operation basically looks like this. So if you see f of x, if you see f plus g in parentheses with an x, what that means is to take the f of x function and the g of x function and add them together. So over here, I have an f of x function and a g of x function. They are simple linear functions, but they are going to be a little bit more complicated in the later examples. But if you are asked to find f plus g of x, you're basically taking what f of x equals, which is 5x, plus what g of x equals, which is x plus 2. So since you're adding, the parentheses are really unnecessary. You just add like terms. 5x plus x is 6x, and then we have a positive 2. So we've created a new function now. F plus g of x equals 6x plus 2. If you are subtracting, instead of a plus sign, you're going to have a minus sign between the f minus g. So when you see this notation, f minus g of x, it means to take the f of x function minus the g of x function. So using these two functions that we were given, f of x and g of x, if f of x is 5x, we would put that first and then minus the g of x function, which is x plus 2. Now be careful when you are subtracting that you distribute the negative, because that's going to change the signs. So we would actually have 5x minus 2, which would then simplify to 4x minus 2. So this f minus g of x is now 4x minus 2. I'm going to get to the domain in just a minute, but let's go ahead and finish our multiplication and division. So if I'm multiplying, it looks like this, where your f and g are right next to each other, and there's really no sign in between, and then you have your x after it. And what this means is f of x times g of x. Now you may also, it's possible to see something like f dot g. So you might see a little multiplication sign of x. That means the same thing. But when we get to our composite functions and multiplication do get mixed up sometimes. So the composite function is going to have an open circle in here between the f and the g, where if you're multiplying, you either just have a dot or nothing at all is typically what you see. All right, so if we are performing this operation, fg of x, that just means that we are multiplying the f of x function, which again is 5x, times the g of x function, which is x plus 2. So if I'm multiplying these two together, I would distribute and get 5x squared plus 10x. So this is my new function, fg of x. And then last but not least, we have division. So if we are dividing, it will look like this, f over g of x, which means to take the f of x function and put it over the g of x function, because when you're writing a fraction, that fraction bar is a division sign. So if, again, in this example, if you're given a function f of x and you're given a function g of x, and you're asked to find f over g of x, you're going to put the f of x function in the numerator and the x plus 2 function in the denominator. And then if you can simplify it, you would simplify it. But at this point in time, we have not learned how to simplify rational functions. So this is a rational equation, which you're going to see in the second half of this class. But one thing now I want to talk about is the domain. So the domain is represents your x values. So what can or cannot x be in this function? So if you have a linear function, like examples with the adding and the subtracting, these are linear functions because you have an x to the first power. If you have a quadratic function, like the one that we got when we multiplied, if you have any polynomial equation, so we could probably make a note here, any polynomial function has a domain of all real numbers. So the adding problem is a linear function, which is one of the polynomial functions. The subtraction is also a polynomial function, so that one will also have a domain of all real numbers. Now you can either write all real numbers. You can write it out, or you can write the symbol, which is kind of like a capital R with a line through it, but you have to write the symbol correctly. There are other ways to write this domain that you'll learn in other classes. So the third one, when we multiply it, again, that's a quadratic function, which is one type of polynomial function. So again, all real numbers for your domain. So it's nice when you have polynomial functions. However, a rational function, which we have here, is made up of a polynomial, a linear function at the top and the bottom. So one thing that you want to make sure that you don't forget is that the denominator, so the denominator can never equal 0. So if you think about what you have in the denominator, x plus 2, so your denominator, x plus 2, cannot equal 0. So what value of x then would make that denominator equal 0? The answer would be -2. So even if we just solve this kind of like a equation, we would get x cannot equal -2. So when it comes to your domain, some textbooks and applications, you can just say x does not equal -2 for your domain. Or you can state all real numbers except, spelled that wrong, x equals -2. So you can write it either like this, or you can write it like this. And again, in pre-calculus and other levels, you'll learn to write it a little differently. All right, so we'll talk more about those domains as we go through these examples. And so in our first example here, we do have a couple of square root functions. So this is your f of x function. This is your g of x function. And you are finding f plus g of x and stating its domain. And then in a little bit, right down here, we're going to evaluate our new function, f plus g of x, for the value of x equals 4. All right, so f plus g of x, like we said earlier, means that you're taking f of x and adding it to g of x. So our f of x function is 5 square root of x. Our g of x function is -8 square root of x. Well, when you're adding a negative, that's the same as just subtracting. But if we also look at the square root of x, these are like terms. So you can think of it as factoring out a square root of x and putting the 5 minus 8 together, which would then equal -3 square root of x. So our function, I'll write that the final answer over here, f plus g of x then equals -3 square root of x. All right, now as far as the domain, so when you think of a square root function, if you think of the parent, y equals square root of x, the parent function has a graph that starts at 0, 0, 1, 1, 4, 2, and it keeps going off to the right forever and ever. The -3 will reflect it over the x-axis and stretch it by a factor of 3. However, when you have an even root, and the square root has a root of 2, that is even. So when you have an even root, if you notice, your x values are always positive. They're going to the right. You cannot take the square root of a negative number, or else you're going to get an I, or imaginary number, which is also a complex number. So we want to state that our domain is going to be everything that's to the right of 0, but also includes 0, because you can take the square root of 0. So it includes 0, it includes everything to the right of 0. So you would say x is greater than or equal to 0. So if it cannot be negative, but it can be 0, and it can be anything positive, then your domain is x greater than or equal to 0. All right, so now that we've found our new function, f plus g of x, and our domain, we are now going to use our new function, f plus g of x, when x equals 4. So basically what this is saying is find f plus g of 4. So we're putting 4 in the place of x, and we're using this new function. So -3 square root of, and we're going to put the 4 in the place of x, and simplify. So the square root of 4 is 2. Oops, it's a -3. The square root of 4 is 2, so when we multiply -3 times 2, we get -6. So f plus g of 4 equals -6 would be how you would answer that second part. So we have our new function, we have our domain, and we used our new function to find a specific value at a certain value of x. The next example we have is a polynomial function. We've got a cubic function here. F of x is 2x to the third plus 4x squared minus 8x plus 4. And then your g of x function is also a cubic function. This time we are subtracting. So f minus g of x, and state its domain. So f minus g of x means that we're going to take the f of x function minus the g of x function. So your f of x function is this whole thing here. So if I put that in parentheses, 2x to the third plus 4x squared minus 8x plus 4 minus the g of x function, which is 3x to the third minus 5x squared plus 6x minus 9. Now be careful when you are subtracting that you don't forget that negative gets distributed and will change the sign of all the terms in the g of x function. So the first f of x function, these signs do not change. So it would be 2x to the third plus 4x squared minus 8x plus 4. But then when we distribute the negative, we're going to get negative 3x to the third. The -5 will become a positive 5x squared, and then the positive 6 will become -6x, and the -9 will be positive 9. So now we combine like terms, and we'll have our final answer. So we've got our 2x to the third minus 3x to the third will be -1, or just -x to the third. You've got your 4x squared and 5x squared. They're both positive, so when we add them together, we get 9x squared. You've got a -8x and a -6x. Combined will be -14x. And then we have a constant of 4 and 9. When we combine those, we get positive 13. So this is our new function, f minus g of x. Since this is still a cubic function, which is one of the polynomial functions, our domain will just be all real numbers. Okay, moving on now to the next example. When you have we're not, actually, it's still the same example. I forgot we're going to be substituting. So it's telling us now to evaluate f minus g of x when x equals -1. So what we're basically doing is finding f minus g of -1. So we're substituting -1 in the function for x. So here is our function. If we substitute -1 for all the x's, I still have a negative in front, but I'm going to put -1 in place of x, and then I'm going to raise it to the third power. We'll come back and simplify that in a second. Plus 9 x squared, and again, replace your x with -1, minus 14 times x again, which is -1, plus 13. Now be careful with -1. When you take a -1 to an odd power, it equals -1. So -1 to the third power is -1. Now you have to multiply it to the negative that's on the outside. But you have to always do exponents before multiplication. So -1 to the third power is -1. Times that -1 will actually end up being positive. The next term, -1 squared. Well, whenever you have -1 to an even power, it will be +1. And when you multiply that times the 9, you're going to get +9. The -1 here is just to the first power, so it's just -1 times -14 will be a +14. The 13 does not have to be multiplied by -1, so when I add those together, I'm going to get 27. 1 plus 9 is 10, plus 27 then will be 37. So to answer the second part, I would say f minus g of -1 equals 37. All right, so we've got our new function, our domain, and f minus g of -1, which equals 37. Now we're ready to move on to example 3. So in example 3, we are going to, again, we're given two functions, f of x and g of x, and we are finding fg of x, which means that we are multiplying. So when there's no sign in between, it means multiplication. So you can either put a little dot in between if you'd like, but understand that that means multiplication, but you don't have to have the little dot in between. But we are also going to be stating its domain. So again, fg of x means take the f of x function times the g of x function. So this is going to bring back some of our rules that we've learned in the past. So x to the third power is your f of x function, and you're multiplying that by the g of x function, which is -5 x to the 1/2 power. So when you are multiplying terms together, you multiply their coefficients. Well, since the x to the third did not have a coefficient, technically it's 1. When I multiply my coefficients together, 1 times -5 would be -5. But be careful with your variables. When you're multiplying variables, you do not multiply the exponents. You add the exponents. And this is where a lot of students make mistakes, so be careful. Take the exponent of 3 plus the exponent of 1/2. We do need to get a common denominator in order to add those together. So I'm going to do that off to the side. So 3 is the same as 3 over 1 plus 1/2. Your common denominator would be 2. So if I multiply the 3 over 1 by 2 over 2, that will now equal, that will give me, I'm going to put an arrow. So that will be 6/2 plus 1/2, which will then equal 7/2. So that is what my exponent is going to be. So I still have a -5 up front, but your x is going to be to the power of 7/2. So that is our new function, fg of x. Now, as far as the domain, again, we have to look at the root. So since we have an even root, just like with the square root, even roots, you cannot take a negative number to an even root. So since x is the only thing that is being taken to this exponent of 7/2, but the even root is very important. So your domain So basically, because there's an even root, that means that x cannot be negative. It can be 0. You can take the square root of 0. And it can be anything positive, but it just cannot be x cannot be a negative number. So to show that it can be positive, it could be 0. It just can't be negative. X is greater than or equal to 0 will be your domain. All right, the next piece of this, we are going to evaluate fg of x when x equals 4. So the notation fg, instead of x, you are now putting 4 in its place. And this is our new function, fg. So -5, but instead of x, we're going to put 4 in its place. We're going to take it to the 7/2 power. So we could do this mentally a little bit. I could rewrite this as a square root of 4. So the bottom number is the root. The top number is the power. So the square root of 4 taken to the 7th power. The square root of 4 is 2. When you take 2 to the 7th power, remember you cannot multiply by the -5 until you've simplified the exponent. So the 2 to the 7th power, actually I don't have that written down, I think it's 128. 2 to the 7th power, yes, 128. So -5 times 128 does equal a negative, where did it go? 640. So going back to the beginning, fg of 4 equals -640. All right, so we could have actually substituted this expression into your calculator just the way it is, the -5 times 4 to the 7/2 power. But it is a little bit tricky substituting it into the calculator. So try substituting this into the calculator, making your exponent 7/2, and see if you get that -640. But if you don't, you can always simplify the square root first and then take it to the 7th power. Okay, so our last example now, we are dividing. So you see this f over g of x. This is our f of x function. It's a linear function. This is our g of x function. It is a radical function because we have a cubed root, or there's a root of 3. And when you're writing f over g of x, that means we are dividing the f of x function by the g of x function. So your f of x function is 4x. Your g of x function is x to the 2/3 power. All right, so you do need to be careful here. Just like with the last problem, when we were multiplying, you multiply your coefficients, and then when you're multiplying variables, you add the exponents. When you're dividing, you would divide the coefficients. Well, 4 divided by 1 is just going to be 4, but then you subtract your exponents. So the exponent in the numerator is 1. The exponent in the denominator is 2/3. So when we take 1 minus 2/3, think of 1 as being, so 1 is the same, minus 2/3 would be the same as 3/3 minus 2/3. So 1 and 3/3 are the same thing. When we subtract, we get 1/3. Also, think of a pizza. If you have one whole pizza and you eat 2/3 of it, how much is left? 1/3. All right, so f over g of x then will equal 4x to the 1/3 power. Now, I will say that if by chance you ended up getting a negative exponent, then you would have to move that x to the denominator. So just be careful to simplify your negative exponents correctly. All right, so this is our simplified function. Now, we have an odd root. So when you have an odd root, you can have negative numbers. You can take a negative number to an odd root. You can take 0 to the odd root. You can take a positive number to an odd root. So if you think of your cubed root, we'll just do a little cubed root graph here. So when we had our parent function, y equals cubed root of x, it went up to the right and down to the left, had this little S curve in between. So you can see your X values do continue to go right and left forever and ever. So your cubed root has a domain of all real numbers. So 4 times the cubed root of X would also have a domain of all real numbers. Oh, wait, that is not true because I forgot. In the beginning, we have an X in the denominator. So this does matter. So in your original function, there is an X in the denominator. So X cannot equal 0 if it would make the denominator 0. If it makes the denominator equal to 0. So if we put 0 in the place of X in our denominator, X 0 to the 2/3 power would be 0, and then 8 times 1 would still be 0. So that would make this fraction undefined. So our domain is really not all real numbers. It's all real numbers except X equals 0. So that's one way of writing it. Or you can just simply say your domain is X not equal to 0, which basically means it can be anything other than 0. All right, so the next piece of this, we are evaluating now the f over g of x when x equals 27. So f over g of x is 4x to the 1/3 power. We have that right here. So now if I'm substituting 27 in the place of x, I'm going to take 4 times 27 to the 1/3 power. And hopefully by now you're recognizing that when you take something to the 1/3 power, it is the same as taking a cubed root of that number. The cubed root of 27 is 3, and 4 times 3 is 12. So f over g of 27 equals 12. Okay, so I do have a special area here where I have different domains that you need to pay attention to. This is the hardest part usually for most students. So I've broken it up into 3 categories: domains or variables in the denominator. So here are a couple examples where we have some functions with a domain or the x value, a variable in the denominator. So if all you have is x to the 1/3 power in the denominator, the only value that would make that denominator equal to 0 is 0 itself. So 0 to the 1/3 power would equal 0, which means that x cannot equal 0. Because, again, anything divided by 0 is undefined. So that's why we cannot have 0 in the denominator. So in this first example, your domain would just simply be x cannot equal 0, or you would say all real numbers except when x equals 0. In this next example, though, if we were to put 0 in the place of x, 2 times 0 minus 3 would equal -3. So putting 0 or substituting 0 in the place of x does not give us a denominator of 0. So what does give us a denominator of 0? Well, if you take that denominator, 2x minus 3, and set it equal to 0 and solve, you would add 3 and divide by 2. So 3/2 would actually be the value that would make the denominator equal to 0. So you would say then the domain would be any x value that is not equal to 3/2. All right, so that's variables in the denominator. So as you're working through these problems, look for any problem that has a variable in the denominator, either at the beginning or the end of the process. So I think right here, see how we had a variable in the denominator, and it's mostly when you're dividing that you'll see that. So if you have a variable in the denominator, you cannot, x will have a restriction of whatever is going to make that denominator 0. So that's kind of the situation we had going on here. All right, the second thing that type of function that you want to be careful of is where is a radical function. So if the variable is in the radicand of an even root. So I've noticed it's only the even roots. Odd roots have a domain of all real numbers, but even roots have to be positive, or whatever's underneath the radical has to be positive. So here we have a square root, which again has an even root. 2 is the unwritten root. Here we have a root of 4. So again, that's an even root. So in both of these situations, we will have restrictions for our domain. But in this first one, whatever is under the radical or in the radicand must be greater than or equal to 0. So when we're stating that, because we have an even root, whatever is underneath this radical has to be positive. It cannot be negative, but it can also be 0. So because you can take the square root of 0, you can take the square root of positive numbers. You cannot take the square root of negative numbers, or else it's undefined or imaginary. So if I just take this statement, or whatever the radicand is, and make a statement, inequality that says x plus 5 is greater than or equal to 0, and then solve by subtracting x to both sides, I now have my domain of x is greater than or equal to negative 5. And if you think about it, when you substitute negative 5, if you were to substitute negative 5 back into the original equation for x, negative 5 plus 5 would give you 0 underneath inside the radical, and the square root of 0 would be 0 times 4 would be 0. So it is defined there. Negative 4 plus 5 would be positive 1. So anything that's bigger than negative 5, like negative 4, negative 3, or negative 2, would be defined. But anything that's less than negative 5, like a negative 6, would then make this negative, and you cannot, again, take the square root of a negative number. All right, so the next one here, the only thing that has the even root is the x. Don't let the negative 9 fool you. This negative 9 is being multiplied by x to the 3/4 power. So it's just x that has the even root, not the negative 9. So what's the only thing that you can substitute in for x to make it equal to x, or to make it equal to 0, and that would be 0 itself. So the only thing that x cannot be, it's an even root. So again, it has to be positive and not equal to 0. So again, we would say our domain would be any x that is greater than or equal to 0. So there's a couple ways that you might see some even roots, written as a radical or written as a rational exponent, and it's the denominator that is the root. All right, so then our third scenario, what if you have both situations? So what if there is a variable that's in the denominator? So if it's in the denominator, then it can't equal 0. And since there's an even root, it cannot be negative. So usually with an even root, it can equal 0. It just cannot be negative. But since it's in the denominator, it cannot equal 0. So it's got two different things that we have to think about. It cannot equal 0 because it's in the denominator, and your denominator, or your x, cannot be a negative number because it has an even root. So in this case, rather than saying x can be greater than or equal to 0, you would simply state x has to be greater than 0. So the only difference is that equal to sign, you do not include it. And there you have your example.